In this video, we will present some key elements of the book chapter, Quantifying Greenhouse Gas Emissions from Managed and Natural Soils, in the frame of the CGIAR Research Program on Climate Change, Agriculture and Food Security. We will focus primarily on measuring the anthropogenic greenhouse gas emissions from smallholder agricultural systems in sub-Saharan Africa. Specifically, we will provide some practical recommendations and introduce some useful tools to implement and optimize chamber-based greenhouse gas flux experiments. Agriculture contributes greatly to anthropogenic emissions of methane and nitrous oxide at the global scale, both of which are strong greenhouse gases. Although associated with low yields, smallholder farms are the predominant form of agriculture in developing countries, contributing to 3/4 of food production in sub-Saharan Africa. In this region, agriculture may contribute up to 80% of the overall greenhouse gas emissions. However, the evidence of greenhouse gas emissions in smallholder agriculture is still very scarce, scattered, and usually constrained to single case studies. One common limitation for assessing greenhouse gas fluxes is the cost associated to the implementation and action of monitoring campaigns. Gas-tight, static chamber approaches allow for measurements of greenhouse gas fluxes at fine scales. Those measurements are rather simple, do not require a power supply or a gas analyzer on site, and make possible the implementation of plot-level experiments. In addition, there are several protocols that already exist that can guide users in the construction of chambers and the subsequent analyses. On the other hand, chambers intrinsically provoke a soil disturbance, cover only a small area of soil, and provide discontinuous estimations of greenhouse gas fluxes, which overall may compromise the reliability of the estimates obtained by applying this technique. However, chambers can provide reliable estimates of greenhouse gas fluxes in diverse landscapes with modest investment and at low operational cost, as long as some key aspects are carefully considered when placing chambers on the plots, when performing gas sampling and analysis, and with regards to reporting and conducting auxiliary measurements.
Gas flux measurements using chamber is rather tedious. For the reason, we should be very careful to think about where to place our chamber in an experimental field to be representative for the given plot. Factors to consider are here terrain, the soil, vegetation, the management, and logistics. Logistics refers to accessibility. How do I finally access my chamber to do the flux measurements, and how will this finally affect properties or affect the management of the site itself? Management is very much about irrigation, fertilization, and compaction, so we should be sure that our chambers represent the major management activities we want to monitor and to see their effects on the greenhouse gas fluxes. Vegetation is very much about as well to think about that we have homogeneous conditions with regard, for example, to the vegetation, or if we go for a crop field, that we not only measure in crop interspaces but also between lines as well, or that we include the crop within the chamber. With soil, we have to think about that even on a small plot, soil properties might change with regard to texture or compaction, so we should check for that before. And finally, we always should think about the terrain, as for example lateral water flow coming from a hillside might affect soil moisture and thus greenhouse gases as well. Following our chamber installation, we should talk about gas sampling. And here we should consider what we monitor and how we monitor, when do we do the measurements, and how do we treat our gas samples with regard to temperate storage, long-term storage, and sampling. With regard to monitoring, we should not only monitor greenhouse gas fluxes itself, but we should also see what is going on within our chamber and outside with regard to crop performance, or for example, if we find ants or termites in our chambers, and we should record that. And then with regard to timing, we should think about when is the best time to sample And normally and usually it's around in the morning hours, as his flux around this time has been found to be representative for the entire day. Once we start to sample with our syringe, we should think about that we flush the vials where we store the gas samples in at least twice the volume the vial has. We should overpressurize, and we should, of course, logically number it itself. While sampling, we should always think about to not disturb the plot too much and be sure that we have a good headspace mixing of our chamber. And then finally, we should think about storage. So, which means we should at first prove that our seals are gas tight, use standards for comparison, and store vials in boxes. Once our gas samples are coming into the laboratory, we should be very clear about responsibilities. So, who is handling my sample? How does he do the reporting? How are data stored? And how is instrument maintenance supervised? We also should think about the measurement instrument. Most important, of course, it's that we optimize for sensitivity in terms of accuracy and precision. We should also have a very good idea about our way how we do flux calculations. We should have a spreadsheet ready to do finally the flux calculations. And we should think about maintenance. So which means we should stock spare parts, we should check and service our instrument regularly, and we should work in a clean environment. Finally, and for sure most important as well, is reporting. So we should do flux calculation immediately, we should report back problems to the team who's doing the analysis, and we should check the logic of fluxes with observations of auxiliary measurements, such as changes in soil moisture and its effect on greenhouse gas fluxes. Only reporting greenhouse gas fluxes for a given field is not sufficient. We need to monitor additional factors to make it really a valuable dataset which can be used by several users. Important parameters to observe and to report on are factors with regard to socioeconomy, management, metrology, soil hydrology, soil properties, and crop and plant performance. The slide provides different examples what should be observed and monitored. Very important is often, for example, management, as those management activities directly affect greenhouse gas fluxes from the soil. Management activities are field operation like plowing and seeding and weeding, application of fertilizers, or irrigation activities. As well, we should know about metrology, which means we should know the temporal changes in the amounts in precipitation, air temperature, and other meteorological parameters. At the same time, we should also observe soil hydrology, for example, with regard to water infiltration, distance to groundwater, or floodwater depths. Important and of outstanding importance for modeling are reporting on soil properties, texture, soil organic carbon, pH, etc. are mentioned here. And as we want to link greenhouse gas fluxes with crop performance, we should also have a very good understanding of our biomass development, leaf area index, harvest index, and yields.
Variability of greenhouse gas fluxes, both spatial and temporal, is a major challenge for obtaining robust estimates at the plot and landscape level. Recently, it has been shown that if conduction of daily measurements of greenhouse gas fluxes is not feasible due to limited resources, sampling more than once a week is still necessary to obtain annual N2O fluxes within 10% of the daily estimates. Greenhouse gas fluxes are also known to greatly fluctuate spatially due to heterogeneous soil conditions, with instantaneous fluxes potentially varying by several orders of magnitude within a few dozens of meters. In order to cope with the spatial variability of soil greenhouse gas fluxes, developing new analytical tools and innovative approaches are highly needed. The gas pooling technique has been proved to be a useful tool for the assessment of soil greenhouse gas fluxes in complex landscapes involving several land uses or land managements, since it provides the opportunity to strongly decrease the number of gas samples needed while absorbing within plot spatial variability. When applying the gas pooling technique, a set of chambers is usually placed at the plot level. Right after chamber deployment, a subsample from each chamber is taken with a single syringe. The gas sample is mixed inside the syringe and subsequently transferred to a glass vial. This constitutes the gas sample at time 0. At fixed time intervals, usually 10 to 15 minutes, the procedure is repeated, generating a total of 4 gas samples, 1 for each interval after chamber deployment. Each of the gas samples will be analyzed via gas chromatography. The change of concentrations with time after chamber deployment will be used for calculating a soil-atmosphere greenhouse gas flux, similarly to the traditional static chamber procedure. The method has been tested successfully in different ecosystems, providing robust and reliable results.
To conclude, chamber-based methods are highly suitable for investigations of greenhouse gas fluxes in diverse and complex landscapes involving several land uses, as is common in smallholder agriculture. The inherent spatial and temporal variability of soil greenhouse gas fluxes appeals for a carefully designed sampling strategy. Our minimum requirements include weekly measurements over a period of a year. QA, QC at all steps of a greenhouse gas monitoring study with chambers is crucial. This includes chamber design and positioning, gas sampling and gas analysis, and flux calculation and reporting. If a number of recommendations are taken into account, robust, reliable data on greenhouse gas fluxes can be generated at a relatively low cost. For further information, we refer the audience to the book Methods for Measuring Greenhouse Gas Balances and Evaluating Mitigation Options in Agriculture, and to the Samples webpage. The CGIAR research program on climate change, agriculture, and food security is carried out with support from CGIAR, fund donors, and through bilateral funding agreements. Thank you for your attention.